Thanks for coming, and I'm happy to share what we've been doing with Harm. Harm is it's capitalized in different ways over time. Sorry, I think I contributed to that confusion, but it is an acronym. Primarily, it stands for highly accurate or high accuracy relativistic MHD. Probably should be renamed now that other more high accurate codes or higher accurate codes exist. But that's what it stood for. But really, it's not the most sophisticated MHD code, but it's been one of the oldest and most widely used, or at least some incarnates of it have been, and it's been kind of a nice, robust environment that we can explore different science questions and topics, and all these people have contributed in some way to some aspect of Harm or its or its associated codes. And I probably have missed some people, so I apologize if I've left your name off. Oh, and yeah, so Harm and its ray tracing cohorts have been used to make this simulation image showing the X-ray emission from accreting supermassive binary black holes. The heritage for Harm started with Zeus. The authors of Zeus wrote. We learned a lot from Zeus and what was good and what was bad. Moving towards kind of a conservative Ganuff scheme framework. The 2D version of the Harm code was written and publicly communicated in 2006. The code paper was in 2003. I helped rewrite the code in a public consumable format with documentation in the 2006 release with the Conda prim routines. But I did not, I was not one of the primary authors of the original code. Then in 2006, Charles Gammy sent me a 3D version of a Newtonian MHD code that he was developing called HAM. Forgot what that stood for. So I took some of the philosophy, data structure philosophy, and then wrote a new version of Harm3D with some of that information, and made Harm3D, which is the version we use. There are other versions of a 3D version of Harm that John McKinney, Sasha Tchaikovsky use. This one's a little different than that. And then in 2012, we adapted it so that it could accommodate dynamic spacetimes. So you could throw in, so it's like a fully covariant code, doesn't care about what coordinate system you're in, what spacetime you're in. You just kind of set that up in a fairly straightforward way, in my opinion, and you let it rip, and it should be able to model plasmas on that spacetime and coordinate system. So as I said, it was one of the first, I think the first successful conservative GMH code for dealing with accretion disks, black hole accretion disks, and it's still publicly available here. You can go to this website and download it. Here, these are the differences between that code and the code we use. I want to start by saying most of the developments have been private. We're going to be publicly making the code available because, well, we should. I fully support open software development, but we're also compelled now by NASA and NSF because we're funded by those agencies, and now they're kind of requiring that all funded projects need to be open source. So we've been meaning to do this for a long time, and I'm glad are twisting my arm to do this. So we're going to be doing this pretty soon. It's just been, I want to make a good user-friendly environment to use the code, so things need to be cleaned and further documented so that users can use the code successfully. I just have not had time to do that, but I will make time soon. So Yeah, so it's written in C. It's pretty straightforward to read, in my opinion. Uses just HDF5, no other bells and whistles, so it's easy to compile. Compiles in seconds and not hours. It's parallelized through uniform or non-uniform domain decomposition, and just uses like PPM reconstruction to do third order spatial reconstruction. Nothing very fancy MHD wise, but it's robust. It has a pretty sophisticated failure recovery scheme, and, so that you can recover from failures on physical conditions and then continue on the simulation. So this is the kind of the ecosystem that has developed over the years around Harm, not entirely always associated with Harm. So for Pandorata is used, to do other things that Jeremy Schnittman wants to do, but it's capable of ingesting Harm data and ray tracing it. It's a Monte Carlo radio transport code. Can do X-ray atmospheres of accretion disks, inverse Compton emission, and then our ray tracer that shares a lot of routines with Harm is it's called Bathros. These two codes, Harm and Bathros, were kind of the foundations of which some of the Einstein Toolkit codes came from. So the ray tracers that they use to create their images that they compared to the Einstein, I'm sorry, did I say Einstein Toolkit? Einstein Telescope project. I used to compare to their observations of the event horizon scale emission around Sagittarius A star and then maybe 7. Then there are other codes that's kind of forked off of Harm. Harm3D nuke. It's not a fork. It's actually just a set of additional properties of the code. Resistive Harm is kind of a fork that we want to kind of reincorporate into the mainstream Harm code. It's a resistive GRMHD code. And then there's Dennis Bowen and Vasily Metas developed kind of a numerical relativity version of Harm. They added a relativistic wave equation into it as a trial to see what adding numerical relativity in Harm would look like. That's something to be explored further. And then we have these infrastructure codes, Patchwork MHD, Patchwork Wave, and also just hydro only Patchwork code called Patchwork that is used to communicate data from one coordinate patch to another. So you can do hydrodynamics MHD or wave equation on a heterogeneous set of coordinate patches that overlap. So at its core, Harm solves the ideal MHD equations in conservative form. There are non-conservative source terms, though. These are the radiative cooling functions that we use to regulate dissipation heat in the disk so that we can explore thermodynamic effects, different cooling rates, different scale heights of the accretion disk. That can play a role in how accretion processes are affected by temperature or different scale heights. So that radiative cooling term is this F, and it's usually just some bolometric isotropic cooling times the local fluid velocity. So it's fluid frame cooling. We're wanting to move past this, but that's what the current state is right now. So this is how things are defined in the code. And so if you look at the code and these equations, you should be able to figure out what's going on. Yeah, and as I said, there's a cooling function, so you can cool to a target entropy or a target temperature profile, depending on what kind of disks or things you want to look at. And those are, and then Harm nuke, which Ariadna is going to be talking about later, it has different source terms, different cooling functions from the neutrino leakage scheme, but I won't be talking about Harm nuke in this talk. And as I said, there's a recovery scheme that there's a logical flow depending upon what fails, what doesn't, that Harm uses to figure out what's the best solution to a problematic state. We have a few of these fix-up trees implemented, but we just typically run with this one. So you check the floor, you check gamma, the Lorentz factor, you check whether or not you should use the entropy equation. So we also evolved in tandem the entropy equation. So if there's a floor condition satisfied, that you use the entropy instead, so that you always maintain a positive density and pressure. Reconstruction methods, not anything crazy. Piecewise parabolic with the MC limiter is what we use by default. And we use the Flex CT scheme from Toth et al. And this reconstructs the EMFs along edges and preserves div B at the corners, not the cell centers. It's a little weird, but you get used to it. Yeah, nothing more to say there. I do want to show you what we can do with it. I think there's a variety of things that Harm and its codes can do. So when we first made it, this allowed us to simulate really thin disks around black holes. This was the thinnest accretion disk simulation for a long time. That resolved the MRI adequately. Maybe satisfies it more adequately than even the thinner simulations that are being run now. Yeah, so and then we're allowed, because we record the cooling rate, we can then post-process the luminosity that is taken away from the disk during the evolution, and give you an electromagnetic prediction of what this accretion disk looks like, its spectrum, its light curve, etc., all in a self-consistent way. One novel thing about Harm is that it's really covariant. So if you take the equations of motion in one coordinate system, they look fairly similar to another coordinate system. So imagine you have space-time, on some space and some coordinate system, and let's say you start deforming them, you actually then transform to a coordinate system that is really uniform in memory. So it's a just simple memory block in your code, and there's a coordinate condition from the memory block in your code to this physical space, and that mapping represents a Jacobian that you applied to transform these vector tensor quantities. And so basically you're solving these things in a uniform memory space, but in reality it's this widely deformed grid on which you have a binary black hole space-time living. So that allows you to do dynamic mesh refinement in a continuous manner and not in a locally block structured format. So you don't have to worry about discrete changes in resolution. They're smoother. Okay. So the dispersion of waves across that boundary may be a little bit more sensible in a continuous transformation in resolution than in a discrete one, due to Gibbs phenomenon, for instance. So we've demonstrated this with MHD. So this is a field loop test that we've used at the same resolution. So warped and non-warped, so uniform and this warped system. So we affect the warp with the field loop. We can maintain better field loop conservation with this. You can see the warping. So because the cells are fixed, the warping means that the boundaries are warped too. That's why you got that phenomenon happening. So this allowed also to simulate binary black hole accretion. So we have those little warps around each black hole. This was our first demo just in hydro of this. seemed to work pretty well. So we did this in MHD, and this allowed us to simulate many orbits and study the mini disk evolution, so the formation of these little disks around each black hole. However, you see this black excision region here because the coordinate system is topologically. It's as you go further out in radius, it looks like a more or less typical spherical grid. So it's topologically spherical. So you have the pinching of coordinate lines at the origin, and that reduces the time step. So it penalizes you. And so in order to remove that penalty, you just excise that region, and you just assume gas flowing into that region disappears. So that's the drawback there, but it allowed us to look to study the mini disks while we were developing other gridding schemes to remove that origin condition. So it allowed us to see how magnetic fields were generated in mini disk evolutions. And then we also developed new metrics, so you can plug and play different metrics. So Luciano implemented this really efficient superposed Kerr shield system where you move around two Kerr shield black holes and make sure that they're boosted, and so it's like a linear combination of black holes essentially. So and then we made sure that they followed reasonable vacuum solutions. So you can look at the fake mass or deviation from the constraints and compare it to our previous space-time, which is called here the matched method, which is a set of post-Newtonian, post-Minkowski approximations that are connected through these matching conditions that we used before in Bowen and all, but are a lot more expensive. And also the superposed Kerr shield systems allows us to investigate spin. So for instance, Luciano compared matched versus superimposed, and we hardly saw any differences. So we started using it and allowed us to include spin and see how Poynting flux was generated from the black holes as they were accreted, and to study variability. And we found that the Poynting luminosity was modulated at 2 times the beat frequency. Beat frequency was between the overdense lump that forms in the circumbinary disk and the binary orbital frequency. And we found powerful, efficient jets that formed out of the mini disk accretion. So the space-time can be dynamic, so why not the coordinate system? Right, we saw with the warps could move around dynamically. We can also shrink the grid. So this is like a regular spherical grid that is shrinking as the binary is shrinking. So this is what we consider a circumbinary disk simulation, where we excise the black hole. So we can take larger steps, but we can evolve the really slow time scale binary shrinkage time scale as it goes from 43M to 12.5M. And this takes many thousands of orbits. And so you want to follow the binary as it inspirals, so you can follow the gas, so you can measure how much gas is there when they merge and maybe brighten up the disk. So this was a simulation that Mark Barra did several years ago demonstrating this. And this is kind of a long movie, but it allows you to, it'll zoom in and you'll see that the black holes are accelerating as they're inspiraling, and the grid is radially shrinking to follow the accretion flow as the binaries merge. So going to the ray tracing code called Bathros, this allows us to back out the light that is lost in the simulation, and allows us to capture it, transport it through the curved space-time in the right way, and then record it at a simulated camera in the distance. So it's a yeah, it allows us to create a simulated image from a simulation. And we use a variety of emission models. We can use self-absorbed cyclosynchrotron emission. So these are emissivity models that are used in the Einstein telescope project. I keep on saying Einstein telescope. I'm sorry, Event Horizon telescope. I'm sorry. If I say something stupid, please correct me. So yeah, sorry, Event Horizon telescope. This is the, the orange donut, picture that people have seen. Okay, I'm sorry, it's the Event Horizon telescope. Yeah, so there are various radiative transfer ray tracing codes used to do this kind of thing, but in the context of low luminosity, radiatively inefficient accretion flows to model M87, SAT-J-star, Cassiopeia-A, that sort of thing. And so they use the emission models that we developed many years ago, and these still remain in Pathros, so you can use them. But we also have other emissivity models like flat body, whatever. You can also you can do like a pixel refinement procedure like AMR to refine really fine features in the image too. So this shows you like the level of refinement across the image to see how that operates. You can do the fast light approximation where you just say, well, the system is frozen in time and you just send your photons through the system, or you can actually step the simulation data in time as the photons are moved too. So Bathros accommodates both paradigms. So the idea is that you have a 3D snapshot of 3D, well, actually 4D set of snapshots of your accretion disk or whatever. You throw photons around through it. You integrate the radiative transfer equation, and that gives you the intensity over your image plane as a function of frequency and time. So yeah, so back in 2007, we implemented a lot of these things in 2D MHD, but we had the ray tracing code, and we also had the emissivity code. And so on the left is an image I simulated of one of these accretion flows modeling SAT-J-star. And you can convolve it with the beam width of the Event Horizon telescope and blur it and kind of simulate what maybe it would look like. Okay, so that's what I did here. So so then when it came out, I searched, I was like, hey, I got these old predictions of SAT-J-star. Does it look anything like M87? And then I compared it. I used the same color map. I had the data, but I had to remake the images because they use a different color map that I did use. So it's like, yeah, it's more or less. So you could have done this 15 years ago. So, but you can also make frequency dependent images of accreting supermassive black holes using MHD data. This is what we did here. So we have some rather ad hoc X-ray corona model here. So this is the hot X-ray bright gas that resides above and below accretion disks. It's very tenuous stuff. You can calculate the spectra and how it evolves in time. You can even record where the photons are from, so you can figure out what components each of the parts are responsible for. So whether it's a cavity, the mini disk, or circumbinary disk. So you can understand that, why is the extreme UV fluctuating so much, and you realize, oh, that's the mini disks and how variable they are. And so then you can compare also what the differences between single and binary accretion disks look like. So maybe you can figure out what if an AGN is a binary or not based on its spectrum, because we haven't really found strong evidence for accreting supermassive binary black holes yet, and we're actively interested in finding them. There are candidates out there. There's this spiky thing called Spiky, that has these really large, possibly lensing flares that are seen. And so we took one of our runs and took like what people thought maybe what spiky is, and we compared our light curve to what spiky shows, and we see fair agreement. So maybe spiky is this, but actually spiky hasn't really reoccurred, hasn't been observed to reoccur yet. There have been problems with observing campaigns and the like. And you can also, so you can use those event horizon telescope emission models and see what you would get with our binary black hole model. Can't really see this very well, but in pink, you see this synchrotron emission coming from the Planck flux, from the jets of the black holes. So possibly these binaries form these double helical jets that emanate from the system, and that could be a way of discerning or identifying them as a binary. So we're also developing more sophisticated radiative transport techniques. So this work that started 10 years ago, Jeremy Schnittman and Julian and I. So we're trying to model the X-ray corona, X-ray emission from these accreting black hole systems. And we changed the accretion rate, and we found that you could transition from a low hard state to a high soft state, which are seen in actual X-ray binaries. Brooks Kinch at Hopkins developed this code called ptransx, which allows you to self-consistently figure out the ionization structure of the flow in the disk that is in equilibrium with the X-ray emission coming back from the corona into the disk and the emission coming from within the disk. So not the whole plasma is not fully ionized. The heavier elements are going to be partially ionized and may result in, for instance, iron K alpha lines that are used to identify the spins or the inner structures of accretion disks. So these are reflection lines. So X-rays hit the disk, reflect off, excite an iron atom, and that excited state then decays and emits an iron line photon. And that line emission then allows us to possibly see it spread through gravitational redshifting, because it has to, some photons, if they're really close to the black hole, are redshifted because of the gravitational potential. But you can also blue shift them if they're coming, if that iron is coming towards you. Anyway, so ptransx handles that ionization radiation balance between the bulk of the disk and the X-ray corona. Pandorata handles the Monte Carlo and the X-ray corona. And so these codes kind of like work together to do the simulation. You can calculate iron line profiles as a function of accretion rate from these MHD simulations. You can, but however, in order to figure out the temperature of your corona, you need the local measure of the local radiation density. And you can do that with Pandorata fine, right? It's throwing photons all over the place from the disk. But maybe you can do this in an ad hoc way that approximates it pretty well, and actually do that cooling self-consistently in the simulation. So right now we do a kind of a post-processing step, but we want to do this all self-consistently. You could kind of like marry Pandorata and Harm together so that Pandorata tells Harm to cool it at this rate. That's an outstanding problem to be solved. We haven't done that yet, but for now we have this approximation scheme that just integrates at each point the emission from the photosphere in some sort of simple geometric way. So that seems to work pretty well. It gives us fairly similar photon energy densities and also similar temperatures in the corona. And we can then look at the X-ray spectra as a function of inclination angle from these simulations. And you can also model the corona as one temperature or two temperatures. So electrons and protons are just thermal equilibrium as one temperature. So now we want to eventually like have Penderata feedback into P trans X, close the circuit, and we've done that too. These are now using the self-consistent cooling and harm, P trans X to find the ionization balance, and P trans X then to give us the light, and we can then, as a function of spin, we've done this for different spinning cases, find the iron line, and these are the first pretty self-consistent predictions of iron lines from including all the physics of the X-ray corona from a MHD simulation. And then we want to do this all dynamically together, have the codes run in parallel together, and we're working on that now. Then there's all the patchwork infrastructure developments. I am not keeping track of time. Does anyone have a clock?
About 5 minutes.
5 minutes. All right. Thank you. We developed the hydro version of patchwork a number of years ago. So if you take different coordinate patches and you do a blast wave test, they perform relatively similarly. Just want to show you this video that kind of visually lets you see how it performs. So if you take a spherical grid and you pass a planar shock wave across it, you'll see that it actually wraps around the pole at the origin, because if you do it naively, I've been told that if you transport the fluxes in some way around the origin, you can get away with this, and it works well. I think this is work by Jeff Ryan. I've not seen it published yet though. But if you do it naively, the origin acts like a pole. The shock wave kind of wraps around it, and you see like there's no shock in this region anymore. It's just been blocked by the origin. But here, if you slap a Cartesian patch over it to get rid of that coordinate singularity, you can then propagate a shock wave across that region. So this could, in principle, solve that problem with the excision sphere in between the mini disks in our binary black hole simulations. But we have MHD, so we need to have this compatible with MHD and magnetic fields. The problem is, well, the divergence of B condition is different in different coordinate systems. So how do you deal with that? Well, if you pinch off and dissipate the field at the interpatch boundary, you can stably evolve a MHD wave across these interpatch boundaries, and it seems to be pretty stable and works pretty well in many cases. We're still writing the code paper, so please look out for that soonish, to be submitted 2019. This is the past. I forgot to change that year. Sorry. So yeah, you can also cover the coordinate singularity at the poles, so that you could do jet simulations without dealing with the coordinate singularity there. Mark has recently submitted his paper demonstrating how this works with binary black hole accretion. So now you can actually simulate the mass flow across the mini disks. You can see this is a movie demonstrating it. You don't see any interpatch boundary phenomenon. So the plasma flows smoothly through the boundaries. We found that actually the mass flow between the mini disks was rather important in the energy budget. So you can get comparable radiative efficiencies from mass like slamming into one mini disk from the other mini disc. And so it's actually really important that we've used Patchwork MHD to study this. You can also in Patchwork you can actually solve different physics. So in the tidal disruption problem, you want to include the self-gravity of the star on its patch so that the star just doesn't puff up and blow away. So you can do this with Patchwork. So this is a Mesa star at half of its life cycle. It's right there. It's that pixel there, that star. It's going to go past this black hole, which is at the center of this yellow circle, which is not the horizon. It's just some inner cutout well outside the horizon. But then the movie, see the pixel moving. It passes periapse. Then gets kind of starts to get disrupted and flies out. See it spreading there. And then after a day, the accretion stream forms, self-interacts, and you can see a lot of dissipation happening at that self-interaction point, and a lot of interesting dynamics at the periapse place.
Can you say something about the grid structure?
Yeah, so it's a spherical grid that's centered at the black hole. The patch around the star is just a Cartesian patch that actually is remapped at certain phases along its orbit. And that was done in Hydra. So the Patchwork wave, so you can measure the wave equation. This is how there's a buffering covering system here. I just want to flash, if you're interested in learning more about this, talk to me. Just want to share these really cool movies. You can transport a Cartesian blocks and another Cartesian blocks, have it rotate and move. You can
I don't know.
The projector itself.
it's a circuit breaker effect, right? No, the AC stopped too, right? I have to do what?
Behind your laptop.
Behind your laptop, desktop.
On this black thing
Yeah, the
here.
remote ones can still hear us. We have to let the projector shutting down again.
Start sharing content.
Yeah, let's go for that. Stand by, I'm starting up. Looks like it.
I guess this is one way to stop an overtime speaker.
You have to share this switch on. There's another one on the
Share HDMI.
Share USB-C.
All right. So here we have three different topologies: spherical and cylindrical, with a Cartesian background grid. You can have that rotating Cartesian grid patch, right? Rotate. You can have a warp, right? Remember the warped grids. So you can have two warps going around on top of another patch in the background. You can have a rotating warp grid. I just thought this was the most wild thing I've seen in a while. So it's a rotating warp grid, and it works pretty well with the Patchwork system. So this is the air of the wave solution on that local patch that is warped, dynamically warped, and also rotating at the same time. And that's my summary. Hope to implement GPU support, make it public, radiation coupling, higher order methods, so we can keep the name. Thank you.
Okay, thank you, Scott. I think we should go on to our next speaker. Should be online or?
So maybe once for the ion line, see in the simulation? Where exactly is it submitted?
I mean, there are contributions. So the corona is bright throughout the domain. You know, its luminosity increases as you get closer to the black hole.
Okay.
There is a plot in the paper that shows kind of as a function of radius that I can show you. But I think it's actually out a little bit outside the history.
Yeah, this is what I would want. Yeah, in the full simulation.
We actually have a little extra time. There's going to be a delay with our speaker starting. And so if you have other questions for Scott, please go ahead and we'll just let you take more questions if we have time. I have a question about the patch, your patch code. Are the grids like overlapping? Do you interpolate between them? Is there anything special you have to do to handle fluxes and stuff between one grid and the other?
Yeah, so they're overlapping in a random way. They can be rotating, so we use a flagging system where we flag how, so there that allows you to see which ones need interpolation or not at those interpatch boundaries. So you don't evolve. So imagine you have a global grid that contains a smaller local grid inside it. The region fully covered, the global cells covered by the local patch are not evolved. So we fill them with the local patch information if we want to visualize it, but they're not evolved in the simulation, so they're not updated. But then there's a buffer region that is interpolated from the local patch onto the global patch. The local patch also has ghost zones that are filled by the global patch. There are kind of flux conditions for the what Mark calls an untethering scheme that deals with the the flux kind of anchoring itself on the interpatch boundary. You kind of have to let go of that flux, else you'll develop stronger and stronger div violations over time. So that's the novel thing for the fluxes at the interpatch boundaries. When the patch moves, you're going to be generating monopoles too. So there's a sweeping procedure that Mark has implemented that sweeps the monopoles back under the local patch region. So the monopoles always are transported with the local patch. A pure hydro run is more forgiving. You don't have to do these tricks, right? And the buffer region can be actually 0. So you can actually have a non-overlapping interpatch boundary that behaves fairly well and just communicate ghost zones from each patch, ghost zone information from each patch. But the wave, patchwork wave requires a much larger buffer region because it uses higher order stencils, 4th order stencils. So you need more, a deeper overlapping region to accommodate that. And so that you're not interpolating interpolated data, right? So you can maintain the 4th order conversions.
Okay. She's good, ready? Okay.